All right, let's talk about static electricity. So first off, what do we already know? Well, we learned from the demonstration that number one, tiny negatively charged particles called electrons can move from one object to another if they are rubbed together. Number two, those electrons will stay in place after they've moved. Well, we will see that that's not always true later on. Number three, those electrons will try to repel each other. And number four, those electrons will try to attract neutral objects. Now, static electricity is a charge that occurs when electrons accumulate on or leave a substance and then stay there. So that's what we saw in our demonstration when I rubbed the balloon against my head. When I did that, electrons moved from my head to the rubber balloon and then they stayed in place. Now, the question is how? Where do they come from? Well, let's take a look at just a general diagram of an object. Now, a neutral object, so an object that has no charge, will actually have an equal number of positive and negative particles. So in the diagram we have here on the right, we've got a blue plus sign that is representing positive particles, and then a red minus sign that represents negative particles. Now, what we learned in the demonstration is that those negative particles are called electrons. Right? Now, if we look at the number of positive charges and negative charges in this diagram, we'll see we've got 8 blue pluses, which add up to positive 8, and we have 8 red minuses that add up to negative 8, and combined, they add up to a total charge of 0. Now, this pair, this positive and negative charge together, that is what is called a charged pair, and that would compose a single neutral particle. Now, we will learn in the chemistry unit that what we're referring to here is actually simply an atom. All right. Now, let's look at two objects. All right. I have here a piece of paper that is neutral. You can see it has the same number of positives as negatives. And over here, I have a piece of what is called acetate, which is just a clear piece of plastic type substance. Now, this also is neutral because it has the same number of positives or negatives. Now, what happens if I were to rub those two objects together? Well, if I rub those two objects together, we've already learned that electrons can move when you rub two things together. So let's see what happens. So after I rub them, what could possibly happen is some of these small pieces of matter, some of those electrons can move from the piece of paper over to the acetate. Now take a look at what that ends up leaving us. We have on this side, we've got 12 positives, but now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 negatives. So we've got more positives than negative on this side, and that means that that's positive. On this side, we have the same number of positives as before, 12, but now we've got 3 extra electrons. We've got 3 extra negatives, so we actually have 15 negatives in here. We have more negatives here, which means this will be negative. So by rubbing two neutral objects together, we ended up with one object becoming positive because it lost electrons, and one object becoming negative because it gained electrons. So let's practice what we just learned here. We have an object here that has 1, 2, 3, 4, 5, 6, 7, 8 pluses, and 1, 2, 3, 4 negatives. What is the net charge? What is the overall charge of this object? Well, we've got 8 positives and 4 negatives, so plus 8 minus 4 adds up to a positive 4 charge. How about this one? We have 1, 2, 3, 4, 5, 6, 7, 8 positives again. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 negatives. So I've got plus 8 and negative 11. So positive 8 plus negative 11 gives us a charge of minus 3. All right, so that's what the net charge is. The important part of it is that this has a positive charge, this has a negative charge. All right, okay, so let's talk about 3 ways we can actually make these electric charges transfer from one object to another. The first is called friction, the second is called contact, and the third is called induction. So we have 3 new ways to actually transfer electric charges: charging by friction, charging by contact, charging by induction. All right, so let's talk about the first one, charging by friction. This is the one that you are actually probably pretty familiar with already. So when different materials are rubbed together or bump into each other a lot, electrons tend to leave one surface and collect on the other. So some examples. You have a pair of socks that you're wearing, maybe some thick wool socks, and you walk across a carpet. Maybe you're dragging your feet across the carpet. When you do that, electrons can leave the socks and move to the carpet. Right? Another possible way that this could happen is if water droplets are in a thunderstorm with high winds. Water droplets will actually gain a charge. When water travels through the air, it actually experiences friction from rubbing up against the air. And when that happens, electrons can move from one substance to another. In this case, they can move from the water to the air, or they can move from the air to the water, depending on some properties of the water and the air. Now, here's another example. I have an ebonite rod and some fur. So here is a rod, here is some fur. Now, if we look carefully, we can see that the ebonite rod has 1, 2, 3 positive charges and 1, 2, 3 negatives. The same thing for the piece of fur. Now, if I were to take this rod and rub it against the fur, that will allow electrons to move from one substance to the other. Now, in this case, it's going to move from the fur onto the rod. So when I rub the fur onto the rod, some of the electrons in the fur will move onto the rod, and as a result, that rod will now have an extra charge. It'll actually have a negative charge, and the fur will now have a positive charge at the end of it. Now, the question is, why would it move from one substance to the other? What causes the electrons to go from the fur to the rod and not from the rod to the fur? Well, we can figure this out based on what's called the Triboelectric Series. Now, when you rub any two objects together, one substance will gain electrons and the other substance will lose. And that is based on basically how strongly those substances want to hold on to their electrons. Right? So substances that have a very weak hold on their electrons will give them away. So when you rub something against them, the electrons will leave. Other substances have a very strong hold on electrons and will try to pull them away from other substances. So whichever substance is higher on this triboelectric series is the more likely one to actually lose electrons. So if you see up at the top, these are the most likely to be positive. So things like air, skin, rabbit fur, hair, wool, that sort of thing. As we travel down further and further and further, these substances are more and more likely to take electrons away and become more and more negative. So something like silicon or Teflon, for example, will very strongly pull electrons away from other substances. Now, there are two basic kinds of materials that we need to understand. The first are what are called insulators, and we looked at an insulator when we were doing the demonstration of the balloon rubbing against the hair. Now, if you rub an object and the charge stays on the spot where you rubbed it, that is an insulator. So the balloon that I rubbed against my head gained a whole bunch of electrons from my hair, and those electrons all stayed right here. They didn't spread out throughout the entire balloon, they just stayed in one space. And so that tells us that that balloon, that substance, is an insulator. So things that fall into that category are things like, as I said, a balloon, which is basically typically made of rubber, something like cotton, fur, that sort of thing. The other type of material are what are called conductors. Now, conductors will allow charges to move very easily through them. Now, typically, we are talking about things like metals. So, for example, copper, gold, aluminum, they are very good conductors of electrons. They are very good conductors of charge because they allow those charges to move through them without any kind of resistance. Right? Now, we can actually determine whether something is a good conductor or is a good insulator based on charts something similar to this. Right? There are a lot of charts that you can find that will give you a lot of detail. This is a very general one, but if you look up on the top right here where we have our conductors, things like silver, copper, and aluminum, these are substances that will allow charges to travel very easily through them. If you look down at the other end, things like rubber, glass, or wood are very poor conductors, which is why they are called insulators. All right. So as we go up this scale, the ability to conduct charges becomes greater and greater and greater. All right. So let's take a look. Example. So I've got this angry person over here, and he's angry because I am about to rub his head with a balloon. And people generally don't like that. Now, I'm going to give him some protons and electrons. So you can see I've given him 4 protons and 4 electrons. So he's neutral, right? The number of positives and negatives are the same. Now, I'm going to do the same for the balloon. And I'm going to give it 4 protons and 4 electrons as well. So it is also balanced. All right, now that we have our protons and electrons on here, what happens if we take our balloon and rub it on our head? Well, I'm going to do this so that we can move everything together, and I'm going to rub the head. Okay, rub the head. And what's going to happen is the electrons are actually going to travel from the head onto the balloon. Now, the reason for that is because the rubber will attract more electrons than what it will get rid of. So now we have a balloon that has way more electrons than it has protons. So that means that this will now have a negative charge. Now, those electrons all, when they traveled over, would accumulate right where we rubbed, right? So when those electrons went from the head onto the balloon, they are all going to accumulate in this spot right here because, again, rubber is not a conductor, it's an insulator. So the electrons aren't able to travel through it. Okay, so now by doing that, we have created a charge on the balloon that is negative right here. But notice that we have also created a positive charge on the head because the electrons over here, or an electron is over here, there's a whole bunch of positive over here, but no electrons, right? So we created a negative charge here and a positive charge here. Now, the second way we can actually give something a charge is through contact. Now, in order for that to happen, we have to have a charged object touch a neutral object. Now, what will happen when we do that is the electrons will actually move to spread out as much as they possibly can. So if I take a charged object and touch a neutral object, the electrons in the charged object can then spread into the neutral object if the charged object was negative, or if the charged object was positive, electrons would move from the neutral object into the positive. Now, what happens when that happens is it can be quick, it can be painful. We've all experienced it before. The example we saw in the first way of charging was rubbing socks against the floor. I'm pretty sure we have all done that before and then walked up and touched somebody and given them the shock. And that was charging by contact. That's a quick jump of those electrons. Now, this is basically an electric shock. So an example, let's say, for example, I have a negatively charged object and I bring it to a neutral object. When I do that, so I've got this ball and I bring it to a door handle, and when the ball and the door handle touch, the electrons are now free to travel from the ball to the door handle. So let's take a look at that. All right, so I'm going to take my balloon that we created here, I'm going to make a copy of it, and we're going to put it over here with the doorknob. Now, again, this doorknob is going to have protons and electrons already. All right, we'll give it an equal number of each. Now, if I take this balloon and touch the doorknob with it, what's going to happen? Well, that means that these electrons here now have somewhere to go. They have a place to actually move, so they will move over here like this. Now, what's going to happen is, when I move it away, if you take a close look,
you'll see that the doorknob now has 3 protons and 5 electrons, so it has a negative charge. The balloon has 4 protons and 1, 2, 3, 4, 5 electrons, so it still has a negative charge. Right? So those electrons are going to spread out, but they're not all going to move. Right? So not all of the electrons that got accumulated would go there. They are spreading out and spreading away from each other as much as they possibly can. And I'll explain why a little bit later. But by touching them to each other, it allows some of the electrons to move, but that means that both objects are now going to have a negative charge. Right? So that's the point that's made right here. If you take a charged object and you touch a neutral object, both are going to end up with that charge. So if I took a negative ball and touch a doorknob, they are both going to end up being negative. If I took a positive ball and touched the doorknob, both of them would end up being positive because some of the electrons from the doorknob would then move into the balloon. Right? All right, so let's take a minute to look at what's called the law of electric charges. All right, so most objects are neutral or uncharged because they have the same number of positive and negatively charged particles. So the same number of protons as electrons. So you, as a human being, are pretty much uncharged because you have pretty much the same number of protons and electrons in your body. Now, the law of electric charges says that any like charges are going to repel. So if I have 2 negatively charged objects, they're going to try to push away. If I have 2 positively charged objects, they are also going to try to push away from each other. Now, if I have 2 oppositely charged particles, however, they are going to attract. So a positive will be attracted to a negative, and a negative will be attracted to a positive. If I have 2 neutral objects, they're just not going to care. Nothing's going to happen. But here's the interesting one. If I have a neutral object and a charged object, it doesn't matter whether it's positive or negative, it's going to be attracted. So a neutral object is going to be attracted to a positively charged object, and a neutral object will also be attracted to a negatively charged object. The question is, why? How does that kind of thing happen? Well, in order to understand the answer to that question, we need to know what charging by induction is. So number 3, the third way we can charge something is by induction. So here's how this works. A charged object can transfer a charge to a neutral object without actually ever touching it. And that may seem weird. It may seem actually impossible. But let's take a closer look. Now, the only objects that this is actually going to work with are conductors. Right? You can't do this with an insulator. And I'll show you why in a moment. The way this works is the charged object, because it has a charge, is going to have what's called an electric field. Right? So a negatively charged object will have a negative field. And that negative field is actually going to push the electrons on the neutral object around. Let's take a look. Let's take our balloon again. And I'm going to put it over here. Now, I'm going to give it some more electrons over here. So I'm going to really build up the negative charge on this. Now, I've got a strong negative charge on the side of the balloon. So that means that if I bring this close to a conductor, it will actually push the electrons in the conductor around. So let's take a look at our conductor. I'm going to put some protons and some electrons in it. Now, I'm going to put the same number of protons as electrons because it's a neutral object, right? So 4 positive, 4 negative. Now, if I take my balloon and bring it close, now remember the rules for these electrons. These ones can't move because this is an insulator, but these ones can. And if I attach a wire to it, these electrons can actually get pushed away and pushed into the wire. So what ends up happening is all of these electrons end up pushed out of our object. Now, not all of them are going to leave, but a lot of them will. And then if I take my wire and to get rid of it, the electrons can't come back. And then if I take my balloon and move this away, I've just got this one little electron in here. So as a result, I end up with this has a strong negative charge. This ends up with a strong positive charge. All right? So, charging by induction. If the object is negative, the electrons are going to repel. If the object is positive, the electrons would attract. So if instead of a balloon with a whole bunch of extra electrons, if I had taken all of the electrons away, the opposite would have happened. If there's a ground, the electrons can then move into or out of the object being charged. So that was our wire. And as a result, we end up with an opposite charge to the originally charged object. All right? Now, here is our laws as a summary. We've got repulsion. So if I have two positively charged objects, they will repel. If I have two negative, they will repel. If I have two neutral, nothing's going to happen. If I have oppositely charged, they're going to attract. And if I have a neutral object, it will be attracted to either a positive or a negative particle. All right, so one final question. What happens when you try to stick a balloon to a wall? Well, if we take a look at a wall, well, let's get our balloon over there first. I'm going to copy that guy over. So I've got a wall here, and I've got a balloon. Now, normally, a balloon doesn't have a charge, and neither does a wall, because a wall is going to be just like any other object. It's going to have, generally, the same number of protons as electrons. Now, if we have two neutral objects, and we bring them too close to each other, law of electric charges says they're not going to do anything. So if you just take a balloon and you put it up against a wall, nothing's going to happen. But if you rub that balloon against your head and you do this, and you accumulate a whole bunch of negative charges on it, when you bring this close to the wall, it's going to push electrons away. Now, the wall isn't a good conductor. Right? So this isn't going to happen easily. So it's not like they are going to just go flying away into the ground or somewhere else. Right? They're going to be kind of pushed back a little bit, but it's still going to stay relatively neutral overall. But those electrons have been pushed away from this section of the wall. And by doing that, it's left behind protons, which gives it a little bit of a positive charge. So now we've got a negative charge on our balloon, we've got a positive charge on this part of the wall, and when we put it up against it, it'll stick. Now, some of these electrons might come out and travel into the wall, but this is an insulator. This is, kind of iffy. It's in between insulator and conductor, but it's closer to an insulator. Those electrons really aren't going to have anywhere to go. So as a result, this is going to keep most of its negative charge, this will keep most of its positive charge, and we end up with two oppositely charged objects. And as a result, this will be attracted to this. Now, it's not perfect. It's not a great negative charge. It's not a great positive charge, which is why you've all seen this before when you rub a balloon against your head and put it up against the wall. Sometimes it works, sometimes it doesn't work great, sometimes it works really well, right? But it's not a great way to make your balloon stick to the wall, because that opposite and negatively charged, those opposite charges aren't very strong, all right? Okay, so that's it for this section.